In this module we are touching the basics of particle acceleration and detection methods. And in this video we'll continue our discussion of particle detection techniques, talking about scintillators and Cherenkov detectors. After watching this video you will know the principle of particle detection by scintillation light and the measurements that can be done via the Cherenkov effect. In scintillation detectors, also called more simply scintillators, particles are detected by means of the luminescence mechanism. Certain materials, when exposed to radiation, absorb energy which is then re-emitted as light. If the light emission occurs soon after irradiation, we call it fluorescence. If it takes more than 100 milliseconds to emit light, we call it phosphorescence. Scintillation corresponds to fluorescence after irradiation by charged particles, high-energy photons or neutrons. There are two types of scintillating materials. Inorganic materials, for which fluorescence is associated to intermediate states due to impurities. They have a high atomic number, so they are well suited for photon detection. And they can be ceramics, glasses, liquids, noble gases and crystals, such as thallium-doped sodium iodide, lead tungstate, or bismuth germanate, also called BGO. And this is an example of a bismuth germanate, a BGO crystal, which is quite heavy. Organic materials are the second type of scintillating materials, and in this the source of fluorescence are excited molecular states. They have high hydrogen content, so they are well suited for neutron detection. They can be crystals, liquids and doped plastics, like this example here. Both have a very short response times, ranging from nanoseconds for organic scintillators to order of 500 nanoseconds for inorganic ones. A particle traversing a scintillator excites the atoms of the molecules of the material, which will then return to their ground state emitting photons. If the material is transparent to at least a portion of the scintillation wavelength spectrum, the photons emitted can be collected at the end of the scintillator by a photosensitive detector, for example a photomultiplier tube, PMT, and often through a light guide. The collected light is then transformed into an electrical signal. The shape of the signal, which is shown in the plot on the bottom, is characterized by the very short rise time, typically less than 1 nanosecond, and a much larger decay time of the order of 100 nanoseconds. The short rise time makes scintillator response faster than ionization detectors. That's why they are used in triggering systems. They have a good efficiency. The energy needed to create a scintillation photon ranges from 20 electron volt for thallium-doped sodium iodide to a few hundred electron volts for doped plastic and BGO. Except for low energies, they are linear. That is, the number of photons is proportional to the energy deposition. Thus, counting photon allows to measure the deposited energy d by dx. Often, light guides are used to transport scintillation light to the photodetector, minimizing losses both by absorption and leakage. They are used to adapt the shape of the scintillator cross-section to that of the photodetector. And here is an example of a light guide. So typically the scintillators will be connected here, and the light will be routed to the photodetector, which will be connected here at the bottom. In some cases, light guides also serve to shift the emission spectrum of scintillation light to better match the spectral sensitivity of the photodetector with what is called a wavelength shifter. These are materials which absorb scintillation light and remit it in a different wavelength. In order to minimize the light losses by reflection, light guides, but as well as scintillators themselves, use total internal reflection. If the incident angle theta of the photon is larger than the critical angle theta c, which sine of theta c is equal to the ratio between the refractive index in R and in the scintillator or the light guides, the photon will not escape by reflection and will reach the photodetector. For plastic, the critical angle is about 39 degrees. At smaller angles, mirror reflection on an external reflector like reflective paint, paper, or special foils like BQT are used. Reflection can be further reduced using glue or gel with the same refractive index to join the elements. And here is an example of scintillator bars which have been painted with white paint to minimize reflection, and then also connected to wavelength shifter fibers which guide the light to the photodetector, which will be connected here at the top. The wavelength spectrum of photons emitted by scintillation has an error of distribution around a maximum. For plastic, the maximum is at 423 nanometers. For thallium-doped sodium iodide at 413 nanometers, at 480 nanometers for BGO, and 475 nanometers for cadmium tungstate, as shown in this graph. Also shown is the detection efficiency for a specific photodetector, a photomultiplier. This quantity is often called quantum efficiency. It is optimum in a certain spectral range, so the photomultiplier must be adapted to the material used. Sometimes a dopant is added to the detection material to shift the wavelength and better fit the photomultiplier sensitivity. The dopant absorbs the scintillation of photons and quickly, that is in less than 1 nanosecond, emits photons with another wavelength. Photons must pass through the scintillator to reach the photosensitive elements. Some photons will be absorbed on the way. The number of non-absorbed photons decreases with distance following an exponential distribution, which depends on the attenuation length of the material, which is generally of the order of 1 meter. And this allows to build large scintillation detectors. The purpose of the photodetector is to convert scintillation photons to an electrical signal, which can be then processed electronically after amplification. Here we show a photomultiplier where the conversion of photons into an electrical signal is achieved via the photoelectric effect in a thin layer of alkali metal alloy called photocathode. The quantum efficiency measures the number of photoelectrons created per incident photon. For modern photocathodes, this is typically 30–40%, depending on the wavelength, as shown in this plot for 2 different photocathodes. Behind the photocathode is a series of electrodes, typically 10 to 14, called diodes. They contain a particular alloy with low ionization energy. An increasing electrical potential is applied. The photoelectrons emitted by the photocathode are accelerated and focalized on the first diode. They release typically between 2 and 5 electrons per photoelectron, depending on the applied voltage. The signal amplification progresses from diode to diode, and the total gain can reach 10 million after 14 diodes. And here is an example of a phototube with metal diodes. Another type of photodetector implements diode as grids, like in this example of a metal mesh phototube, which you see is much more compact than the the phototube with metal diodes. So let's now see how the Cherenkov effect can be used to detect particles. A charged particles of velocity v going through a medium of refractive index n will polarize the atom along its path. These atoms become electric dipoles and emit electromagnetic radiation upon returning to their ground state. If the velocity of the particle does not exceed that of light in the medium, radiation of the dipoles of the upstream and downstream sides of the path cancel. If, on the contrary, the velocity of the particle v is larger than c over n, where c is the velocity of the light in the vacuum and n is the refractive index of the medium, the downstream material cannot be polarized. The electromagnetic field created by the particle propagates less quickly than the particle itself, and the net radiation results. Its wavefront forms a cone of light around the path of the particle. This is the Cherenkov effect. And this kind of radiation is produced in all transparent media. The energy loss by Cherenkov radiation is negligible. There are mechanical analogies to this mechanism, which is like a boat in the water or a plane which exceeds a velocity of Mach 1. The radiation threshold is then beta larger than the inverse of the refractive index of the medium. At threshold, the radiation is emitted in the direction of the particle, that is at theta equal to 0. The different threshold for charged particles with different masses can be exploited to differentiate between them, for instance, to identify different isotopes. Particles heavier than m max will not emit radiation. Ring imaging Cherenkov, called RICH, go a step further. Here the Cherenkov light is intercepted by a detection surface. Photons form a ring which allows to measure Cherenkov angle and thus determine the velocity of the incoming particle. In addition, the intensity of the Cherenkov light, that is the number of photons in the circle, is proportional to the square of the particle charge. Cherenkov light is also emitted in water. This gives the possibility to build large mass detectors like the Super Kamiokande in Japan. This gigantic water tank surrounded by photomultipliers is used to detect neutrinos. In the next video we will see how the different detectors are combined to form spectrometers and calorimeters.